All right, yeah, so hi. So today, first of all, we need to finish the classification of orthogonal operators in terms of rotations and reflections, okay? Let me begin by recalling what we have obtained so far, and then we'll conclude by combining these results and ideas, okay? So last time we have proved theorem 646, okay? So let me recall. This says that if V is a real inner product space, okay, which is non-trivial, and the dimension of V is finite, okay, so under these assumptions, let T be a linear operator on V, which is orthogonal. Okay, so again, remember, orthogonal just means that it preserves distances or norms of the vectors. Okay, in this case, there exists pairwise orthogonal T invariant subspaces W1 through Wm for some number m less or equal than the dimension of V, such that we have two things. So first, we have that the dimension of each of these spaces, Wi, is between 1 and 2. Okay, so this holds for all I from 1 to m. And B, we have that the whole space V can be written as a direct sum of the W's. Okay, so the direct sum of W1 through Wm. So this is the first result that we have proved, the decomposition of V into a direct sum of pairwise orthogonal invariant subspaces, all of dimension 1 or 2. Okay, and then we used earlier results about orthogonal operators on inner product spaces of dimensions 1 or 2 to further deduce additional information about this decomposition and about how the restriction of T behaves on each of the W's. So this was theorem 647 prime. Okay. So given this V, T, and W1, Wm, like in theorem 646, we then have additional properties. So this decomposition further satisfies part A, the restriction of T to each Wi is either a rotation or a reflection. Okay, so this happens for each I from 1 to m. Next, we have that the number of the subspaces Wi for which the restriction Twi is a reflection is even if and only if the determinant of the operator T is equal to 1, and odd if and only if the determinant of T is equal to -1. So we have these two possibilities. And finally, C, we can moreover choose this decomposition, the subspaces W1 through Wm, a bit more carefully to ensure that there's at most one reflection appearing on this list. Okay, so it is always possible to choose such W1 through Wm, the subspaces of V, invariant whose direct sum is all of V, yeah? So subspaces satisfying all of these previous requirements, such that moreover, the number of these subspaces Wi, for which the restriction TWI is a reflection, is 0 or 1. So we need to use at most one reflection among all these restrictions. Okay, and again, this corresponds to whether the determinant of T is equal to 1 or it is equal to 0. To minus 1, excuse me, not 0. Of course, yeah, we only have 1 or minus 1. Okay. Yeah, so, and finally, if we have, so we know that TWI is a reflection for at most one I, right? So if it is for some WI, then the dimension of the corresponding space is 1. Right? So each of these WIs has dimension 1 or 2. And for the one, for at most one, which possibly has a reflection on it, the dimension is going to be 1. Okay, so we finished last time with the proof of this. Okay, so we finished proving this result. And now, finally, we can obtain the desired presentation of an arbitrary orthogonal operator as a composition of rotations and reflections. So this is going to be the corollary to these two theorems. Okay, so the situation is the same. So we assume that V is orthogonal, not orthogonal, excuse me. V is a real inner product space. T, a linear operator on V, is orthogonal. And as usual, the dimension of V, of course, is finite. Yeah, so the same assumptions. Okay, then there exist orthogonal operators T1 through Tm, so finitely many orthogonal operators on V, such that we have the following conditions. Part A, for each I from 1 to m, the linear operator Ti is either a reflection or a rotation. So each of the Ti's is one of these two. Part B, for at most one I, Ti is a reflection. Okay, so reflection appears only once in this list of operators, or at most once, more precisely. So it could be 0 or 1. Yeah, we have this. C, we have that all these operators commute. So we have Ti composition with Tj is equal to Tj composition with Ti for all Ij. So all these operators are pairwise commuting. D, so finally, we have that T is the composition of the Ti. So it's the composition of T1, T2, etc., Tm. And the last point, E, which tells us the behavior of the determinant. So the determinant of T is going to be 1 if Ti is a rotation for each I from 1 through m, and it is going to be -1 otherwise. So otherwise meaning that a reflection appears somewhere on this list. All right, So this theorem is the desired classification of orthogonal operators. Yeah, because we start with T, an arbitrary operator on a real inner product space, which preserves distances. And what the theorem shows, so in particular part D, is that then this operator can be obtained as a finite composition of rotations and reflections. No matter what you started with, right? It's only rotations and reflections. And moreover, reflection you have to use at most once. Okay, so this is the main result that we are working towards for a couple of lectures. So finally, we are ready to gather the fruits of our labor and finish the proof. Okay, so let me pause for a second so you can have a better look at this statement, and I'm going to continue to start the proof on the next page. Okay, so let's prove some of this. So proof. So we're going to use all the information from the theorem, theorems 647 and 646. Okay, so by 646, we can take W1 through Wm, a decomposition of T. So meaning that these are invariant subspaces of dimensions 1 or 2, etc. Yeah. So I'm just applying this. And moreover, I'm going to also use the part of theorem 647C. The part C which tells us that we can use at most one reflection in this process. Yeah. Okay. So by these results, so we can write that V is equal to W1, direct sum with W2, etc., direct sum with Wm, Wm, where we have additionally that Twi is a rotation for all I less than m. Okay, so what it's telling us is that at most one operator is a reflection. This we know from 647C. And now I'm just saying, let's take these subspaces in such an order that the possible reflection is going to be in the last position. Right? So the order doesn't matter. We can pick the order of the subspaces, like you find them, and then if you need, you can reorder them. We know that there's at most one of them, restricting to which T is a reflection. So make it the last one in the list, just enumerate it in that order. Okay. All right. So what, at least this guarantees that we have a rotation for I below M, and for Tm, we are not saying what it is. Could be rotation, could be reflection. Okay. So now, for each I from 1 through M, we define Ti, a linear operator from V to V, as follows. So I'm going to take Ti of x1 plus x2, etc., plus xm. I'm going to take this to be x1 plus x2, etc., plus xi minus 1. Okay. Now I'm applying t to the i's coordinate. And after that, again, I'm not doing anything. So I get xi plus 1, etc., xm, where we have that xi or xj, better because we're already using the index I. So xj belongs to the subspace wj for all j. All right. So I'm defining the operator ti like this. How do we know that we can reorder them? Yeah, simply because we can look the previous result. So theorem 647 C tells us that we can choose such a decomposition where all but at most one are reflections, right? Okay, so of course this one reflection might appear in any position on this list, but nothing prevents us to just then take them in a different order. The sum is still going to be the direct sum, right? Because if you have some subspaces whose direct sum is the whole space, if you permute them, it's the direct sum in this alternative order is still going to be the whole space. Because it's a reflection. Yeah, so we know reflection appears somewhere at most once. Maybe no, it either appears nowhere or appears at somewhere at most once. So if it appears, I change the order of the subspaces in such a way that it appears in the last position now. I just permute the subspaces. It doesn't change anything, yeah? All right, so, okay. So now let's go back to the definition of this operators Ti. So we have defined Ti like this. Now, this defines a map from V to V, yeah? So are we all cool with this? Yes, direct sum is commutative. That's another way to say it, yeah. So you can take the order of the subspaces and direct sum in any order, yeah. So we have, let's make sure that Ti is indeed a map from V to V, okay? So why do we have this? Well, because we know that V is the direct sum of these subspaces, right? It's the direct sum of these subspaces. And so then it means every vector in V, so every vector X here is going to be of this form. So it's going, we know we can write it as a sum of Xj, where Xj comes from the Wj on this list in the direct sum. So this tells us that this map Ti is defined on every vector in V, right? So this tells us that it is indeed a map from V to V. And now we're going to say, to claim that it has a bunch of additional properties. So claim the map Ti is a rotation or reflection on V if and only if the corresponding restriction of T to the subspace Wi is a rotation reflection. Well, in the same order, excuse me. So reflection, rotation. Okay. So let's be careful here for a second. So the map, the previously defined restrictions of T to the subspaces, this is a map from, remember, this is a map from Wi to Wi, right? Because Wi is an invariant subspace. So when we take restrictions, a map from Wi to Wi. The difference now is that we define Ti using this map, essentially, because we only apply it in the corresponding coordinate. But Ti is a map from V to V, yeah? So it's important. We define Ti as a map from V to V, but associated to the restriction, as you will see in a second. Yeah, well, as this claim says, for example. Okay, so this claim follows from the definition of rotation and reflection, right? So prove the claim follows from the definition of reflection or rotation on V with the subspace in the definition given by Wi. Right. So if, for example, if TWI was a rotation, this means that Wi had dimension 2. And this Wi served as the corresponding subspace for rotation of the whole space, right? In the definition. Because remember, in the definition of rotation, we say there exists a two-dimensional subspace on which it satisfies the certain formula given by the rotation matrix. Okay, but if we knew that TWI was a rotation, then this Ti defined in this way is going to satisfy that with respect to this, because when we look at the vector corresponding to the subspace Wi, on this subspace, it acts like the restriction So it acts exactly like TWI. So it means that it is a rotation. But on all the other vectors, it acts like an identity, right? So if I take a vector in the orthogonal complement of WI, then TI is just going to be an identity on it. It's not going to do anything to a vector. And this is precisely the definition of what it means to be a rotation with respect to the subspace WI. And similarly for the case when we have a reflection. Yeah, so the properties, we get this corresponding properties of TI directly from, by translating these properties of the restriction TWI that we have established. And so this claim, it immediately tells us that parts A and B hold. So the claim says that gives us parts A and B. Because we knew that there was at most one TWI was a reflection. So this is what gives us part B. And part A also, because each restriction TWI was a rotational reflection. And so by the claim, the same is true for TI. Okay, and the parts C, so this gives, so the claim gives A and B. Okay, and now parts C, D, E are on the homework. So this is a homework exercise. Okay, so the main point is to realize that in fact we can write T as a composition of the TIs, but this you can see from the definition. Yeah. Okay. So that's why this is a corollary. Somehow the main meat of the theorem is actually contained in theorem 646 and 647. And now we just need to compose things correctly. So here how TIs are defined. Okay, so this concludes, well, this partially concludes the proof, modulo the homework. Okay, so we have this, yeah? So this tells us that, this provides us this nice geometric picture of orthogonal operators, because we start with a very abstract definition, which is just saying that all distances are preserved. Okay, a priori, there could be many very complicated ways to preserve a distance when you act by linear operator. But this classification theorem tells us that, in fact, all of this is just built by repeated rotations and maybe using a reflection once. All right. So, okay. So this concludes the proof of this. And we are moving to a new topic. Well, let me pause for a second. If there are any questions about this first, let me know. All right, if not, let's move to the next topic, which of course, again, is still interconnected. So the topic, you might have seen it, but now we're going to develop all of this rigorously with proofs. So the topic is the Jordan canonical form. Of a linear operator. So let me start with some motivational words. Yeah, I see some excitement in the audience. Yeah, okay. So we start with some motivation. Yeah, so what is this about? So recall something that we know very well, and we've used it a lot. Yeah, so we know that diagonalizable linear operators have a particularly simple description in terms of the matrix. Okay, so as we all know very well by now, such operators have diagonal matrix representations with respect to some basis, right? So such operators diagonal matrix representation or equivalently, there exists an ordered basis consisting of eigenvectors. So equivalently, admit a basis of eigenvectors. All right. And we know that once you choose such a basis, so that the matrix is diagonal matrices are very easy to work with algebraically, right? We know like they're easy to multiply, easy to transpose, etc. Yeah. So it's a very nice matrices to work with. So the problem, however, is that most linear operators are not diagonalizable. Yeah, so tough luck, are not diagonalizable. Okay, so of course we could stop at this and say, okay, there's nothing you can do, yeah, but that's not how math works. You try to identify maybe some presentations which are not as nice as diagonal matrices, but so that maybe they're still not too far from it, so that maybe we can still analyze them in terms of matrices which are diagonal or close to diagonal. And this is going to be our aim, is to understand or obtain nice matrix representations for more general operators. Okay, and especially we will tackle the case, so we will do it for the case of operators whose characteristic polynomial splits. Okay, so this is going to be the level of generality. We are going to look at operators with splitting characteristic polynomial. Now, why is this good? Or why is it general? Well, because if we are over the complex numbers, then in fact, this is true for all linear operators, right? So in particular, if f is equal to c, the complex numbers, then our results will apply to all operators. Okay, so we will prove indeed a rather general theorem, at least when the field of scalars is the complex numbers. All right, so now let's try to start. So first of all, we need to come up with some generalization of diagonal matrices. Okay, and for this, Jordan blocks and Jordan canonical form are what come into the picture. So as you will see, this is more general than diagonal matrices, but also hopefully you see that it's maybe not too far. Like it's still such matrices still have rather simple structure. So namely, assume we have T, a linear operator on V, where V is a vector space of finite dimension over some field of scalars F. Okay, and assume that beta is a basis for V, or ordered basis for V, such that we can write the matrix representing T with respect to beta in the following special form. Okay, so it's a matrix which consists of blocks. So it's a block matrix. It consists of square blocks on the diagonal, which we will write as A1, A2, etc., up to AK, and we have zeros everywhere outside of the blocks on the diagonal. So such that we have each AI is a square matrix of the form. So it can be a 1-by-1 matrix, and in this case, it just has one entry, lambda. Yeah, so it's either a 1-by-1 matrix with an arbitrary value, lambda, or it is a square matrix of the following form. So it looks like a diagonal matrix. We have lambda, lambda, etc., lambda on the diagonal. We have zeros below the diagonal, but it is a little bit non-diagonal because we also have a single one above each lambda on the diagonal. and we have zeros everywhere else. So let me maybe insert one more here. So it means we have 1 here, we have 0 here, and we have zeros everywhere else. Okay. So each block AI is of this form for some eigenvalue lambda of t. All right. So this is assume that our matrix looks like this, a special form. So it's a matrix consisting of square blocks on the diagonal and zeros everywhere else. And each block is either just a 1-by-1 matrix with an eigenvalue of t, or it's a matrix of this form, which is a slightly non-diagonal matrix with lambdas everywhere on the diagonal. All right. So such a matrix AI, so a matrix of this form, is called a Jordan block. Jordan block corresponding to the eigenvalue lambda. Okay. The whole matrix is then called, so the matrix T with respect to beta is called the Jordan canonical form of T, or for T. Okay. And finally, any beta, a basis beta, so that the matrix with respect to it is a Jordan canonical form, is called a Jordan canonical basis. So this is a Jordan canonical basis for T. Okay. So we have this new kind of matrices, which are a bit like diagonal ones, but not just as good. So they consist of blocks, and each block is almost a diagonal matrix, except for these ones above each entry on the diagonal, where you can have it. So note the first entry on the diagonal is lambda. There's nothing above it, so we don't put anything above it, yeah, because it's the entry in the position 1, 1. Okay. And of course, if T looks like this, we know from earlier, then this means that T beta, excuse me, is in fact just the direct sum of the matrices A1 plus A2, etc., plus AK. Okay. So Jordan canonical form is just a direct sum of Jordan canonical blocks. Okay. So this is a definition. Yeah, this is just a definition. We are not saying that such presentations exist. We are not saying anything so far. We just define a new special kind of matrices, which sometimes maybe appear and sometimes don't. So our task will be to demonstrate that indeed such presentations are possible to choose when the characteristic polynomial of an operator splits. Just to give you a little spoiler. Okay, so let me record a remark, which I think I already said basically, but let's make sure, let me reiterate it because it's important. So observe that each Jordan block AI is almost a diagonal matrix or close to a diagonal matrix. Oops, diagonal matrix. And we have that T, the matrix representing T with respect to beta, is diagonal if and only if each block AI is of the form consisting of of the form 1-by-1 matrix, which just has the eigenvalue lambda in it. Okay, so a diagonal matrix is also indeed a Jordan canonical form, right? just because any diagonal matrix can be viewed as consisting of blocks AI, where each AI is just a one by one matrix, which contains the corresponding entry on the diagonal. So we see that diagonal matrices are a special kind of Jordan canonical forms. But Jordan canonical forms are more general. So let's consider an example, more concrete example for a second. So suppose, which will also illustrate some of the phenomena that we will have to deal with. So suppose we have T, a linear operator on the space C8, okay? So the number bigger than usual appearing in an example. Okay, so the field of complex numbers, the standard vector space C8, and assume that beta consisting of V1 through V8 is an ordered basis for the space, for the vector space C8, such that we have that if we let J be the matrix denoting T with respect to beta, representing T with respect to beta, okay? So assume that this matrix looks as follows. So this is just going to be an example of a Jordan canonical form. Okay, so look, this is indeed a Jordan block, because I just have twos on the diagonal, and I have ones above the diagonal and zero everywhere else. Then I have a block consisting just of a 1 by 1 matrix with one entry 2. Then we have a block 3, 1, 0, 3. So this again, a Jordan canonical block. And we have 0, 0, 1, and 0. Okay, and we have zeros everywhere else. So assume that this is a canonical form, or Jordan canonical form. Sometimes I might omit saying Jordan, but it's better not to do it. So Jordan canonical form of T. Okay, so assume we're given an operator which has this matrix with respect to some fixed basis, V1 through V8. Okay, then the characteristic polynomial of T can be calculated quickly from this matrix, right? So by definition, the characteristic polynomial is given by the matrix representing T, J, minus the variable T times the identity matrix I. Okay, so now we can calculate it. So this is a block matrix. So we know that the determinant of a block matrix is just the product of the determinants of the blocks, right? So we can write it then as the determinant of the matrix 2 minus T, 2 minus T, 2 minus T. So the same things on the diagonal. Now we have 1 above it, 1 above it, and we have zeros everywhere else. Times the determinant of the second block. So now this block, this is of course just 2 minus T, matrix with a single entry 2 minus T, times the determinant of the next block. So this is going to be the determinant of 3 minus T, 1, 0, 3 minus T, and finally times the determinant of the remaining block. So we take, this is the block, and then I subtract T times the identity matrix, right? So what we get is minus T, minus T. Here I have 0, and here I have 1. Okay, now if you do the calculations, what we get is the polynomial of the form T minus 2 to the power 4 times T minus 3 square times T square. So this is the characteristic polynomial. Hopefully we all know how to calculate it by now. You just, if you're given a matrix, yeah, then we just calculate it like this. Okay, so now what can we say about the multiplicities here in this picture? So the multiplicity of each eigenvalue, remember, the multiplicity is the power with which the corresponding monomial appears in the splitting of our characteristic polynomial. Yeah? So the multiplicity of each eigenvalue is the number of times it appears on the diagonal of J, right? Because, for example, the multiplicity of the eigenvalue 2 corresponding to the first polynomial. So we have 2, 2, 2, and 2 4 times, right? And the power here is also 4. And the same applies to all the other eigenvalues. So in this example, we can notice this special property that the multiplicity of which eigenvalue corresponds to the number of times it appears on the diagonal in the canonical Jordan form. Okay. Also, in this example, we can observe that the vectors v1, v1, v4, v5, and v7, these are the only vectors in beta that are eigenvectors of T. The only vectors in the basis which happen to be the eigenvectors of T. And this again we just see from checking the, well, since we know the characteristic polynomial, we can verify this. Okay, so this is the only eigenvectors of T, and they correspond to the columns of J, with no one above the diagonal. Okay, so indeed note that these are the vectors v1, v4, v5, v7. So for example, if you look at v1, this corresponds to this column. So here we have the entry on the diagonal, but there's no one above it because there's nowhere to put it, right? Next we have v4. So this is v1, the column corresponding to v1, this is the column corresponding to v4. Again, we know that there are zeros everywhere here. So in particular, we have zeros here. So there's again no one above it. On the other hand, if I looked at this one, for example, there's no one above it again. So this is v5. Yeah. And the remaining one is v7, this one. So again, there's no one above it. All the other ones have a 1. The diagonal entries in all other positions, like if I look in this position, I have 1 above the diagonal. In this position, I have 1 above the diagonal, etc. Okay, so we notice this simple correspondence in the picture that the vectors in the basis, which are eigenvectors, they appear in the columns with no 1 above the diagonal. And as we will see later, this is not a coincidence. Okay, so the idea is just that the example illustrates some of the things which are special for the Jordan canonical form. So we'll see that these two of these observations, they in fact not coincidental, and that they're true in general for Jordan canonical forms. Okay, so the aim of what we are trying to prove is that we will show that every linear operator whose characteristic polynomial splits admits a Jordan canonical form. So this is going to be the main aim of this part of the course. Okay, to show that this always happens. So this will require some finer analysis of cyclic subspaces, etc. So you will see soon. But before that, let's consider another example. So let's say this was example 1. Let's consider example 2. Okay, example 2. It's important to point out that Jordan canonical form of an operator is not determined by its characteristic polynomial alone. So the Jordan canonical form of a linear operator T is not determined by the characteristic polynomial of T. So what do I mean by this? So you'll see in the example in a second. So assume T prime now is some other linear operator on the same space, C8, as example 1. But let T prime be such that the matrix T prime with respect to beta is given by J prime, where beta is the same basis as before. So beta is an ordered basis from example 1. Okay, and we have that J prime looks like this. So it's a matrix which is a diagonal matrix now, and the entries on the diagonal are 2, 2, 2, 2. Then we have 3, 3, and then we have 0, 0. So I actually drew it bigger than needed. Okay, like this, and I have zeros everywhere else. So this is my diagonal matrix. Okay, and T prime is going to be the operator corresponding to this matrix representation. Okay, so you see the matrix is different, the operator is different, but we have that the characteristic polynomial of T prime is the same. So it's also going to be 2 minus T to the power 4, 3 minus T square times T square. Okay, just because we can calculate the characteristic polynomial from this matrix, it's easy to see that it's going to be the same. But of course, the matrix J is not equal to the matrix J prime. So this means that we have two different Jordan canonical forms. Okay, so these examples illustrate that we can have two different canonical forms which give rise to the same characteristic polynomial. So it tells us that the Jordan canonical forms depends on the operator itself and not just on the characteristic polynomial of the operator. Okay, also let's make a couple more observations in this example. So the characteristic polynomial is the same, but also from J we have, so looking back at the matrix J in example 1, we have that T of V2 is equal to V1 plus 2V2, right? Just look at the corresponding column at the second column of J. This tells us what happens if you apply T to V2. So we have that T minus 2I, so I is again the identity operator, of V2 is equal to V1. Similarly, we have that T minus 2I of V3 is equal to V2. And we have that V1, V4 are eigenvectors of T with eigenvalues lambda 2. So we have that T minus 2I cube of Vi is going to be 0 for I equal to 1, 2, 3, or 4. Right? So in each of these cases, we see that we get 0. So here we have, right? So you see here we have 0, 0, 0, etc. Okay. Similarly, if we calculate, we get that T minus 3I square of Vi is going to be 0 for I equals to 5, 6, and T minus 0I square of Vi is going to be 0 for I equal to 7, 8. Okay, so you see that we are noticing some general principle here. So we see that we can always find some power. So the T minus lambda, an eigenvalue lambda, times the identity matrix to this power gives us 0. So so far we just checked it in this example. But let me finish quickly with formulating the general principle that happens here in a Jordan canonical form. So if V lies, if V lies in a Jordan canonical basis, for a linear operator T on V, and we have that its column in the matrix T with respect to beta has diagonal entry lambda. Okay, then we have that such a formula holds, so T minus lambda I to the power P evaluated on V is equal to 0 for sufficiently large P. Sufficiently large natural number P. And moreover, eigenvectors satisfy it with P already equal to 1. Okay, so the different, as we saw in the example. So for each eigenvector, we already have that this is true for power 1. So we could put 1 here and 1 here. And we get that we already get 0 with 1, right? But in general, we only guaranteed that there exists some power which gives us 0, like this, some power P. Okay, and the proof of this proposition is in fact also a homework problem. So, yeah, you'll have a chance to think about it. But the idea that we observed this property in the examples, and now we see that in fact this is a general principle. Okay, so next time we'll see how to utilize this observation, like what can we actually get from this, okay? This leads to a certain notion of generalized eigenvectors. But okay, we'll discuss it next time. So I'll stop here today. Yes, sorry, I think I took a bit longer again. Yeah, thanks everyone for coming. All right, thanks everyone, bye.